Okay, so start of a new unit, limits and continuity. Again, this is the start of a calculus curriculum, but hey, this is pre-cal BC, so we've finished the pre-cal stuff. We're going to start the calculus stuff. This first page, I'm not even going to go over this. Miss Murray said if we have time we might, but it's just ugh. Yeah, I just put that on video. This is the formal definition of a limit. If you take calculus in college, some of you will just bypass it altogether. They might start with this. And it's kind of a pain because you look at like all the letters and the symbols and the stuff going on. The short answer is we're not going to do that. Turn the page. Let's start with a more conceptual, less formal understanding and explanation of limits. Far more intuitive than the it's called the epsilon delta definition. Okay, limits. The concept of a limit is the entire backbone of calculus. And that is absolutely true. Once you're a couple weeks into calculus, you don't use limits a whole lot because you're doing derivatives and antiderivatives. And you're going to memorize a whole bunch of shortcuts for derivatives and antiderivatives. But the definition of those things is a limit thing. So we have to know about limits to build up to derivatives and antiderivatives. Without limits, calculus would not exist. Absolutely, that is true. And without calculus, we wouldn't have gone to the moon, cell phones, microwaves, ultrasounds, TVs, radio, tons of things result from calculus. There are, students and even administrators are always introduce a real-world application of what you're learning. You're like, well, it's kind of hard. In calculus, it's pretty easy to give the real-world applications of what we learn. But it starts with limits. Think of a limit as the intended height of a function. Not necessarily the actual height, but where are we headed? What are we approaching? What is the limit of this function? The height of a function is its y value, but a limit is the intended height, the function we're headed toward. Another way to say it is, it's the value that the function thinks it's going to. That's kind of a weird way to phrase it. When we get to the graph, that'll make more sense. It might get there, it might not. We don't care. We only care about what the value is approaching. That's its limit. Okay, so consider this function, x cubed minus 3x squared, graph for you. The height of the function changes as x goes from left to right? So we're going up, we're going down, we're going up again. Increasing, decreasing, increasing. That's all calculus stuff. Look at what happens to the height as x goes towards 1 from the left of 1. So here's x equals 1. As x is approaching 1, my y is approaching negative 2. And then look at what happens as x goes towards 1 from the right. So from this side, well, then my y value is also approaching negative 2. As x heads toward 1, y heads toward negative 2. Now, that is not how we write limits. We'll write them more formally in a minute, but that's the idea of what's going on. As we're approaching an x value, what's the y value getting close to? Approaching an x from the left to the right is called a one-sided limit, right? Because you're only coming in from one side. Here's how we write that. The limit as x approaches 1 from the left, so that from the left is why that little minus sign is there. Maybe that looks weird. It's a little superscript minus sign. It's not an exponent. It just means a little less than 1. From the right, we put a little plus sign there. Approaches 1 from the right. So looking at what we just did, the limit as x approaches 1 from the left, we said that was negative 2. And from the right, it was also negative 2. Now, this next statement might seem like not a big deal, might seem obvious. and I guess it is obvious, but it's super important. If the limit from the left is equal to the limit from the right, then that limit exists. So this one's negative 2. I say that because there are times when they're not the same. Like the limit from one side is not equal to the limit from the other side. Yes. Like if there's a jump or if there's an asymptote, they're not always the same. Turn the page. Let's see. So consider that equation and its graph already given it to us. Why is there a hole at 2, 4? Must be something going on with that denominator. Sure enough, if the factors cancel, that puts a hole at 2. So I guess the answer would be, why is there a hole there? Because we had factors that cancel. That makes a hole. Okay, the limit as x approaches 2 from the left. So the left side of 2 means we're headed this way. I don't care about what value we get to at 2. I care about what are we approaching as x approaches 2. So what is the height that we're approaching? 4. And even though we don't get there, we still have an equal sign there because limit means approaching. So we don't have to put like a squiggly equal sign or an arrow. Like limit means approaching. So we are approaching 4. On the other side, as we come in from the right, we're also approaching 4. Are they the same value? Well, yes. So that means that limit is 4. Even though that the actual function doesn't even exist there. Another way to write that would be f of 2 equals, what does f of 2 equal? Right, undefined, D and E, doesn't work, divide by 0, like all those things. There is no function at 2. And yet there's a limit there. Does not exist. Undefined. All right, let's think about this piecewise function. Limit as x approaches 2 from the left. All right, what do you think? We've done enough of these, even though we haven't done many of them. As x approaches 2 from the left, what is the function headed toward? What's the intended height? 4. And as x approaches 2 from the right, we're headed toward 5. So what do you think the limit is as x approaches 2? If we don't have a side on there, there's usually 2 guesses that people give. One of them's right, one of them's wrong. What's the overall limit? 5. Okay, 5 because there's a dot there. That's not the right answer, but I see what you're thinking. 4.5 because that's the average. Also not the answer.
1 because it's 1 apart from
It's easier than all of those. It doesn't exist. It doesn't exist. They have to be going to the same point for the limit to exist. So there's not a silly rule about bigger or filled in dot or average. Nope. If they don't go to the same spot, then it doesn't exist. Okay, some practice. And these are kind of grouped. Not kind of, they are grouped. So there's some stuff at 1, some stuff at 6, some stuff at 2. Let's do the ones together, and then I'll let you try the rest on your own. X approaches 1 from the left. So x approaches 1 from the left. So that would be right there. What's that answer? What are we headed toward? 7. How about from the right? also 7. So what's the overall limit as x approaches 1? 7. And g of 1 equals? Well, look carefully. There's a hole at 7, but there's a dot at 2. So g of 1 equals 2. All right, I'm going to hit pause and let you try the remaining, 10 problems? So there's those answers for the rest of that. Any questions on those? Well, we went 9 for 10. That's 90% on our first go. That's pretty good. I'll take that. Limits of infinity, limits at infinity. So let's be careful here. We always lump those together when we teach them, but they're not the same thing. Limits of versus limits at. Of infinity basically means when y is headed to infinity. Limits at infinity is when x is headed to infinity. And I guess I should say plus or minus, so we could be going either direction infinity. All right, they were kind enough to spot us the graph here. As x increases without bound, what is the height of the function approaching? So as x goes way, 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 way out there, can you tell by the graph? You might be able to tell by the equation. What is our function approaching? 1/2. Maybe it's a little hard to tell on the graph because it's right in the middle. But this is top no, bottom O, equal co. Did we talk about that in here?
Yeah.
Okay. So this is an equal co problem. That's a limit at infinity because x is headed toward infinity as x goes to infinity. If a limit as x goes to infinity exists, then it's a horizontal asymptote. Again, so we could put up here, this is the top no, bottom O, equal co stuff. So you use that for limits as x goes to infinity. You can use kind of the cheat code there. If a limit as x goes to negative infinity is a real number, then it's also a horizontal asymptote. Here's a question that we mislead you on frequently. Shame on math teachers everywhere. Can a function cross a horizontal asymptote?
Yes.
It's like, yes. Yes, it can. Because you're only worried about what happens as x gets really, really big. Just as an aside, you still can't cross a vertical asymptote. I mean, that's a different lesson entirely, but a lot of times when we're teaching vertical asymptotes, we say you never cross an asymptote. And that's not quite right. You never cross a vertical asymptote. You can cross a horizontal asymptote. Okay, so here's the fancy looking stuff for the same thing we just said. As x goes to infinity, if the limit exists, like if it's just really a number, 7 or 3 or negative 12, then that's a horizontal asymptote. Because you're getting closer and closer to that number. That's what an asymptote means. Same thing on the other side, as x goes to negative infinity, this would mean your y value is approaching k. If your y is approaching something, that's what a horizontal asymptote means. Okay, some more practice problems here. Consider this graph. There's the graph. Limit as x approaches 4 from the left. Limit as x approaches 4 from the left. Ooh, we better be careful here. 4 on the left side of 4. So that would be down here. We haven't done one of these, but what do you think that answer is? Negative infinity. And then 4 from the right, so we're a little bit more than 4. So we're coming in from this side. Positive infinity. What do you think the limit is as x approaches 4? Definitely does not exist. Now, all of these does not exist. So this gets a little confusing just on like classifying our answers. Infinity and negative infinity are special cases of D&E. There's a couple reasons limits don't exist. We saw one of them already. If they go to different things, so if the left and right are different, that's one. If they go to infinity, we officially say that doesn't exist, because infinity is not a number. So, and this gets a little confusing because it's like, well, which answer do you want, infinity or D&E? And on multiple choice, we could put it either way. So it's best to understand that it's both. It's positive infinity, which means it's D&E, or it's negative infinity, which means it's D&E. When a limit from the left to right goes to infinity, that's a vertical asymptote. We can see that by looking. A limit is equal to infinity, that limit doesn't exist. Oh, here we go, I answered this already. Can a function cross a vertical asymptote?
No.
Definitely not. Hard no. Because vertical asymptotes come from zeros of the bottom. Actually, let's just look at the one that... So x can't be 4. Like, period, amen. Like, you can't divide by 0. You start learning all these math rules, and then they sometimes start stacking up on each other, and you're not sure which one's more important. You can't ever divide by 0, so x can't be 4, so you'll never have something cross or on a vertical asymptote.
What is it?
Okay, this is fancy talk for what we just said. If we're headed to plus or minus infinity, there's a vertical asymptote wherever that's happening. Okay, some summary comments here. Every one-sided limit exists unless the limit is infinity or negative infinity. So for one-sided limits, you always can have an answer. Your answer might be infinity or negative infinity. For a regular limit, meaning thinking about both sides, if there's a whole, the limit exists and is the y value of the whole. We saw that already, so this isn't new information. This is supposed to be like summary of things we already saw. For a regular limit, not one-sided, if there's a break in the graph, the limit does not exist. A lot of times we call that a jump. It doesn't matter where it's filled in or not filled in. If there's a jump, that limit doesn't exist. The one-sided limits exist, but the overall limit doesn't exist. The limit as x approaches infinity or negative infinity gives you a horizontal asymptote. Remember, that's the top no, bottom O equal co stuff. And then if you get infinity, it's a special case of D&E. In fact, another way to phrase this is, here's the cases of D&E. Maybe we should do it this way. Start with the D&E and when might that happen. The first way we saw was if there was a different left and right limit. A different left and right limit. Then that overall limit wouldn't exist. A second type of D&E is the infinity stuff. So we would still want you to say infinity, but also know that it's D&E. And then there's a third type that we haven't really looked at, but I want to go ahead and say it. And that is if the graph is oscillating. There's some really tricky examples of this, but there's also a really easy example of this. The limit as x goes to infinity of sine of x. Think about what the graph of sine of x is doing. Some of you just trace it out in the air there. up and down and up and down and up and down forever and ever and ever. So as we go farther and further out, we're not approaching anything because it's oscillating. So that one's pretty rare, but in the spirit of giving you all of the information, we'll just go ahead and say it. It comes up occasionally in calculus, even then it's still pretty rare. But I think you would, I hope you would have said what is going on there, because there is no limit. It's not approaching anything. Let's see. Do we want to do all of these? Probably not. Let's do 1 through 4, and I'll pull some more popsicle sticks. For someone looking later, there's the answers for those 16. If you're watching the video, press pause because I'm about to move on. The only thing. The main thing to be careful of is make sure you're looking at the correct graph. Right? Like that's where people make mistakes, is not really finding a limit, but just looking at the wrong picture. So be careful. So why don't you try 31 and 32? Try 31 and 32. Not that we doubted Katie. We should have known. Okay, 37. Well, it looks terrible, but it's not really that bad. I will say, not tested, but I do want to do a couple of these together because these are interesting. Should probably put them on a bonus, but I don't know if we will or not. Determine the value of the limit as x approaches 1 of h of x, or explain why it doesn't exist. Okay, be careful. H of x, there's not a picture for h of x because it's f of g of x. As x approaches 1. When we have parentheses in math, where do we usually start? In the middle, on the inside. So let's first find the limit as x approaches 1 of g of x and see what that is. Okay, so let's make sure we're looking at the right picture. G, the limit as x approaches 1. It's just negative 1. Right? I mean, there's a hole there, but that doesn't matter. The limit from both sides is headed toward negative 1. So let's see what's happening. So that's sort of like g of x is headed toward negative 1. So now let's see what f is doing as g is headed toward negative 1. So, well, as the input to f, so as the input to f is headed toward negative 1, okay, we think it does not exist because it's different from both sides. But back up to our g, as we approach, as x approaches 1, g of x is approaching negative 1, but g of x is always coming from the top, so it's always a little more than negative 1. It's always a little more than negative 1, so that means our input to the f function is always a little more than negative 1, meaning from the right. So that means our answer is negative 1 from the right would be 2. So that's kind of tricky. You can't just evaluate and plug it in. You've got to really be thinking about left and right on those. Why don't you try B, and then we'll be done with this worksheet. So limit as x approaches 6, k of x is g of f of x. So we switch the order, so be careful. So try B. Look at f first, and then look at g. They're kind of goofy. Be careful with those. Okay, so you got the worksheets.